Hello and welcome to General Astronomy Lecture 5, Patterns in the Night Sky. So up until this point, we've mostly just looked at the history of astronomy. So we started out looking at what the ancients saw and believed in their time, and then we brought ourselves up to speed a bit in terms of modern astronomy. So what we're going to do now is kind of take a look at what we see ourselves today. So this is an exciting time in the history of astronomy. We have a new generation of telescopes that are scanning the depths of the universe. We have increasingly sophisticated space probes which are collecting new data about our planets and other objects in our solar system. We are undergoing some rapid advancements in computer technology and are allowing scientists to analyze the vast amounts of new data and models so that we can process and predict things that occur in planets, in stars, and galaxies, and even the universe as a whole. So in this lecture, we'll start to take a look at a few key ideas that will help us to understand what we are seeing in the night sky. Shortly after sunsets, as daylight fades to darkness, the sky appears to fill with stars, unless you're near a bright city. On a clear, moonless night and far away from a city with lots of light, more than 2,000 stars may become visible to your naked eye. And if you are out far enough, you might even see the whitish band of light that we call the Milky Way. So in this image here on the right, you see that whitish band of stars. This is an image that I took near Sardis Lake, Oklahoma, in southeast Oklahoma. So, if you go out far enough, you might be able to see something like this. As you look at the stars, your mind may group them into patterns that look like familiar shapes or objects. So this is something subconscious that we might even be doing. You look up at all these different dots, and a couple bright ones might look like a certain shape to you or to your mind. And so your mind naturally groups them. If you observe the sky night after night or year after year, you will recognize the same patterns of stars. The patterns have not changed noticeably in the past few thousand years. So, although from minute to minute or hour to hour or even day to day, what you see in the sky might differ. It might move across the sky. But as you come back to the same location a year later, you'll see the exact same thing you did the year ago. So, although things are moving in our night sky, it doesn't seem like the stars themselves, at least relative to us, are moving very much at all because we still see the same patterns over and over again. So we'll get into a little bit of why that might be. First of all, people of nearly every culture gave names to patterns that they saw in the sky. We usually refer to such patterns as constellations, but to astronomers, the term has a more precise meaning. A constellation is a region of the sky with well-defined borders. The familiar patterns of stars merely help us locate constellations. So this is actually a common misunderstanding, is that a constellation is not a pattern of stars. A constellation is a boundary or bordered region in the night sky. So although you might be familiar with Orion and Orion's belt here, when you say, I'm looking at the constellation Orion, you're not necessarily saying you're looking at the pattern that you see here. You're actually calling out the boundary, the layer or region, of the night sky that you're looking at. So just be careful. A constellation technically does mean a region of the sky. And again, the patterns we see only help us differentiate between them. So just as every spot of land in the continental United States is part of some state, every point in the sky belongs to some constellation. So you can almost think of constellations as states of the night sky, or the sky in general. So it turns out that our modern sky, on modern star charts, the entire sky is divided into 88 regions, or constellations. So every single point of space is contained within some constellation. Now again, these are not physical constructs, they're not physical regions in space. They're just imaginary boundaries we set to define a certain region. And this helps us with navigation. So maybe you're saying, hey, I found this really neat star. I'm looking at this through my telescope. And somebody says, oh, well, where is it? and you could probably respond simply with Orion. It's in the Orion constellation. And suddenly, the person you're speaking to knows at least what region to look at in the night sky. And then you can give some more technical details if you need to. So, for example, the constellation Orion is now defined to be a irregular patch of sky whose borders are shown in the figure at the center. So we've seen this already. So here is the outline of the shape of Orion, which is supposed to represent a human, which you see on the right in this artist representation. You can see the similarity between the two. And on the left, we have the actual physical stars. So this is what we would see through maybe a long exposure photograph or multiple layered photograph. So all of these different constellations do have historical significance. So Orion did represent a hunter, you can see with a club, and to the top right of Orion is the constellation of Taurus, which you can't really see in this central image, but you can see the artist's representation of the ball here on the right. So this is a common theme that goes throughout all of the 88 constellations. You can see many of the other drawings kind of scattered around in this image. So for the most part, this just helps us with navigation in the sky. The stars of a constellation only appear to be close to one another. So they aren't necessarily physically right next to each other, even though to our own eyes it looks like they may be. Usually what we see is only a projection effect. The stars of a constellation may be located at very different distances from us. So as an example, in the Orion constellation, which I've been referring to multiple times already, you can see distances labeled in light years from Earth to 4 different stars in the Orion constellation. Although Bellatrix, which comes from the Arabic term for Amazon, and Mintaka, which is for the belt, they do appear to be close to one another, right? So here we have Bellatrix and we have Mintaka. In the night sky, they are very close to one another. But as the labels show, they are almost 600 light years away from one another relative to us. So the two stars only appear to be close because they are in nearly the same direction as seen from Earth. This same illusion often appears when you see, for example, an airliner's lights at night. It is very difficult to tell how far away a single bright light is, which is why you can mistake an airliner, which is only a few kilometers away, perhaps for a star that is trillions of times more distant. And this image here on the right is trying to give you an example of how this projection effect might work. So here we are on Earth, and we might see the Big Dipper, right? This is a very common group of stars that people refer to in the night sky. It's easy to point out, but that's not what it actually looks like. Many of the stars are very far away from one another. So even though it looks like, this Big Dipper, these stars are very far away from one another, and they might not actually be in that shape. So that just gives you a nice example of how this might work, and it gives you a visual of this projection effect. Now, as I've mentioned, constellations can help you find your way around the night sky. For example, if you live in the northern hemisphere, which many of us do, I believe all of us do, you can use the Big Dipper in Ursa Major, which is the constellation Ursa Major, so right here is the Big Dipper. You can use that to find the north direction by drawing a straight line through the 2 stars at the front of the Big Dipper's bowl. So here's the 2 stars at the front of the Big Dipper's bowl. If you draw a line through them and then continue that line, you will point, the first moderately bright star that you point to will be the star Polaris, which is the North Star. It's called the North Star because it is located almost directly over Earth's North Pole. So if you draw a line from Polaris straight down to the horizon, you will find the north direction. So that's a great navigation tool for us in the Northern Hemisphere. Find the Big Dipper, use it to point to Polaris, and that is north. So, if you ever get lost, maybe that can help you. Now, during winter in the Northern Hemisphere, you can see some of the brightest stars in the sky. Many of them are in the vicinity of what we call the winter triangle, which you can see here at the top. So, this connects the bright stars in the constellations of Orion, which is the hunter, Canis Major, which is the large dog, and Canis Minor, the small dog. A similar feature, which is the summer triangle, which you see in the bottom image, graces the summer sky in the northern hemisphere. This triangle connects the bright stars in Lyra, which is the harp, Cygnus, the swan, and Aquila, the eagle. Now, I'm not going to ever make you memorize constellations. That a lot of students come into this course thinking, astronomy is about constellations. I'm going to have to memorize all of these constellations. I don't actually believe I ever have you memorize any of them. Astronomy goes much further than this. In fact, we only touch on the ideas of constellations in these couple slides, and we don't talk about it again. But again, in this lecture, we're just trying to show and discuss what we see ourselves before we go out and try to discuss the specifics of all these different objects. So just be aware that you won't ever have to memorize these different constellations unless you, on your own time, become an amateur astronomer and you use telescopes to point things out and all that. Then you might want some star charts and to become more familiar with these. But for the course, at least, you're okay. You don't need to memorize them. So I mentioned previously that stars or patterns might move through the sky from night to night, but the actual pattern of the stars doesn't change over time. Well, if you go outside soon after dark, you'll find a spot, and if you find a spot away from bright lights, and note the patterns of stars in the sky. And you do this again a few hours later. You will find that the entire patterns of stars, as well as the moon, assuming it's visible, has shifted in position. New constellations will have risen above the eastern horizon, and some will have disappeared below the western horizon. If you look again before dawn, you will see that the stars that were just rising in the east, when the night began are now low in the western sky. This daily motion, also known as diurnal motion, of the stars is apparent in time exposure photography. So this motion of stars and objects in the night sky based on daily motion is called diurnal motion. And this image here on the right, it's not a standard photograph like you might expect. This is what we call long exposure photography. So the photographer in this case left their lens open for a long period of time, and as a result, as the stars moved across the night sky, this person's camera picked up that, and we got something that we call star trails. So this is a long exposure photograph, and you can see the motion of these objects now, right? If we look at the night sky, we don't see these lines or streaks in the sky. We see points. We see the stars. But you can see their motion in this type of photography. So it's, I think, one of the neatest ways to take photography is to do something like this with long exposure. But anyway, to understand diurnal motion, note that at any given moment, it is daytime on half of the Earth, right? So half of the Earth is illuminated by the sun, and then it's nighttime on the other half. So no matter what, there's always a bright half and a dark half of the sky. Of the Earth. So the Earth rotates from west to east, making one complete rotation every 24 hours, right? This is where the day comes from. It is a daily cycle of day and night. So the Earth rotates about an axis constantly. So the sun is always illuminating half of the Earth, whereas the other half is dark. Because of this rotation, stars appear to us to rise in the east and set in the west, as do the sun and moon. Right? So stars aren't physically moving across the sky relative to us. We're just rotating, and they appear to move because we are on the moving Earth. All right. Now, if you repeat these motions, if you repeat your observations on the following night, you will find that the motions of the sky are almost, but not quite, the same. The same constellations rise in the east and set in the west, but a few minutes earlier than on the previous night. So, let me go back for 1 second. I forgot to show this slide here. I forgot that I had it hidden behind an animation. So this just shows the rotation of the Earth again, right? So here's the Earth with light coming from the sun on the left, and the Earth is rotating counterclockwise. So, for example, if you're in California at 8 p.m., so just after the sun sets, you might see Cygnus overhead. But a few hours later, so now it's midnight, well, now Cygnus is way off to the right, and Andromeda is seen overhead. So this is that daily or diurnal motion, right? The Earth is rotating about its axis, so as a result, you might see Cygnus overhead at 8 p.m., but just a few hours later, you see something different overhead. So Cygnus will have moved across the sky relative to you. So that's the diurnal motion. So again, I apologize for missing that slide. Okay, so let's continue on then. So the same constellations rise in the east and set in the west, but a few minutes earlier than on the previous night. So each night it shifts by a few minutes. If you look again after a month, the constellations visible at a given time of day, say maybe at midnight, will be noticeably different. After 6 months, you will see almost a totally different set of constellations in the sky. Only after a year has passed will the night sky have the same appearance as when you began. This happens because of Earth's orbit around the Sun. Over the course of a year, Earth makes one complete orbit, or revolution, and the darkened nighttime side of the Earth gradually turns towards different parts of the heavens. Right, so we have diurnal motion, which is the daily motion of stars in the sky caused by our rotation about an axis. But we have this changing in rise and set times of different constellations over months because of our motion around the sun, our orbit. So as it said, the night side of the Earth faces different parts of the night sky at different times throughout our year. So hence, the particular stars that you see in the night sky are different at different times of the year. So this figure here on the right shows which constellation is overhead at midnight local time when the sun is on the opposite side of the Earth from your location. During different months for observers at mid-northern latitudes, so that includes us here in the United States. If you want to view the constellation Andromeda, the best time of the year to do it is in late September. So here we are in September. The dark side of the Earth in September faces toward Andromeda, so it's a great time to view it. So that's a great way of looking at this. So if you go a couple months later, so say from September to November, well, now Andromeda is way off to the right, so you're barely going to see it at nighttime. But now it's good to see Perseus, right? And then this completes, so this is only half of the image, but it's a full orbit. So, on the other side, we might not see Andromeda at all at night. So we see different sets of constellations throughout the year. So it'll take an entire year now from September to come back around and see Andromeda directly overhead again. So that gives you an idea of how this might work. So, in the previous slide, we showed that these differences from night to night are about 4 minutes apart. So they rise about 4 minutes earlier than on previous nights. So here's a question for you. If the constellation of Cygnus rises along the eastern horizon at sunset, so you can come up on your own with a time that you think sunset might be, at roughly what time will it be highest above the southern horizon? So take a few moments to think about this. Pause your video as you think, and then return when you're ready. All right, well, we first of all know that Earth rotates once in 24 hours. So when the star of Cygnus, or the stars of Cygnus, rise in the east at sunset, they take about 12 hours to go from one side of the sky to the other, right? Half of the motion. So as a result, it takes about 1/2 of that time, or about 6 hours, for stars of Cygnus to move halfway across of our sky. So thus, Cygnus will be highest in the sky around midnight if you assume that sunset's around 6 p.m., depending on what time of the year it is. Right? So let's, again, say sunset's at about 6 p.m. We know the Earth rotates all the way around once in 24 hours, which means the stars of Cygnus would take 12 hours to go from rising in the east and setting, and setting in the west. So it takes 12 hours to complete its circuit across our sky. So for it to go half that motion to be highest above the horizon, that would take half of that 12-hour time, or 6 hours. So we would see this at about midnight. So it's a little bit more involved. So try to review this and really think about this. Maybe go back and refer to some of our images that we've shown if you're a little bit confused. But that gives you an idea of how you can do some of these calculations pretty simply, maybe just in your head. Anyway, now we can finally talk about what this celestial sphere actually is. You heard me mention this a few times in our history lectures, so now we can actually discuss it now that we've established an idea of how to describe things in our night sky. So the stars in a particular constellation appear to lie close to one another, but we know now that they might actually be really far apart in reality. That's because they may lie at very different distances from Earth. This illusion only occurs because we lack depth perception when we look into space. It's a consequence of the fact that stars are so far away. How can we tell something's 9 light years away as opposed to 10 light years away? We don't really have a means to do that because of our lack of depth perception at such great distances. So the ancient Greeks misunderstood this illusion to be reality. They mistook it. So they imagined that stars and constellations lied on a great celestial sphere that surrounded the Earth. So they thought there was an actual physical sphere around the Earth with all stars lying on it. Now, that is not true, of course. We know that there is not some weird sphere around us. But, nevertheless, the celestial sphere is a useful illustration because it allows us to map the sky as seen from the Earth. For reference, we identify 4 special points in circles on the celestial sphere. So these images, so I can even go back, it doesn't matter much, just give you an idea of what this celestial sphere looks like. So it's an imaginary sphere around the Earth. We have the North Celestial Pole, South Celestial Pole, all the same things just like on Earth. And here's just another view of this celestial sphere with a lot of the constellations mapped onto it. And even here you can see the Earth, you can see the sun's position through time across the celestial sphere. We call this the ecliptic, which you'll learn about soon. So this is that celestial sphere in a graphical form. So it's very important to us, and we are going to use it now to define some important things. So although it is not a physical construct, it's still useful to us because we can map things with it. So 4 important points that you're going to hear about are the North Celestial Pole, which is just the point directly over Earth's North Pole. Doesn't get much more obvious than this. So here is Earth's North Pole. So on the celestial sphere, the North Celestial Pole is just directly above that. Following that same idea, the South Celestial Pole is the point directly over the Earth's South Pole, down here. The celestial equator is a projection of the Earth's equator into space. So here's our equator here, represented by the black line. So the celestial equator is the same thing, just extended out onto this sphere. And as I mentioned, we do have something called the ecliptic. This is the path that the sun follows as it appears to circle around the celestial sphere once per year. It crosses the celestial equator at an angle of 23.5 degrees. And that's because the tilt of the Earth's axis is 23.5 degrees. So you'll hear this a lot, the term ecliptic. So remember that that is the path of the sun through the sky and that it's angled at 23.5 degrees. You'll hear that number referenced a few times as well. So the point in the sky directly above an observer, so it doesn't matter whoever's looking out into the night sky, the point directly above you is what we call the zenith. So as you move across the Earth, your zenith changes position. Your zenith is different from everybody else's zenith, but it's just a name that we give the point directly above the observer. The zenith and the celestial sphere for an observer at, for example, 35 degrees north of the equator is shown to the right. So this is actually almost about where we are. We're almost 35 degrees above the equator here in Durant, Oklahoma. So this is just a graphical representation of that. So the zenith appears at the top of the figure here, directly above our observer. So the Earth appears to be tipped in this figure. And in the image at the bottom here, I just gave you an example of some more star trails where you can actually see the North Celestial Pole right here. All the stars rotate around it. So just a neat picture of another star trail that I figured I'd include. So continuing on with this, for an observer that is anywhere in the northern hemisphere, the North Celestial Pole is always above the horizon. So again, you can see that here in the image at the top right. As Earth turns from west to east, it appears to the observer that the celestial sphere turns from east to west. Stars sufficiently near the North Celestial Pole actually revolve around the pole. They never rise or set. And so we call those stars circumpolar stars. So any of these stars right in this circle I'm trying to highlight with my cursor, we would consider all of these stars to be circumpolar. They circle the pole and they never rise or set. Any of the other ones, like all these down here, are all setting or rising at some time. So they would not be considered these circumpolar stars. Stars near the South Celestial Pole never rise above the horizon at all either. All other stars do have daily circles that are partially above the horizon and partially below it, which means they appear to rise in the east and set in the west. So this image here at the bottom just tries to show you what these star trails would look like if you were at different places on the Earth. So at middle northern latitudes, where we are, stars appear to move at some angle to the sky. But if you were at the North Pole, the exact North Pole, of course there's a little polar bear here just for fun, if you were to look at the horizon, you would see stars move directly from left to right as the Earth rotates about its pole, which you're at. But if you're at the equator, you would actually see stars moving straight up and down. So you can almost kind of catch that here. You would see that if you were a little bit further south. So just a neat way to show this. So people that take these long exposure photographs at different parts of the Earth will see different things. So it's really neat. Okay, now let's get into a little bit of some more technical details here. We won't go into the math too much, but you will see a little bit here. So our lack of depth perception on the celestial sphere means that we have no way to judge the true size or separation of objects that we see in the night sky. However, we can describe the angular size or separations of objects without knowing how far away they are. An angle measures the opening between two lines that meet at a point, right? So this is an angle here. There's two lines that are meeting at a point. So this angle we would say is half of a degree, which is the unit that we use to measure angles. So this is a good way to help explain some of these things. So the angular size of an object is the angle it appears to span in your field of view. So I'm going to go back and forth between these slides as we discuss this idea. But for example, the angular size of the sun and moon are each about half of a degree. So if we go back to here, well, here's the angular size of the moon. It appears to take up an angle of half of a degree. And although we know that the sun is much larger, it's also much further away. So surprisingly, it actually takes up about half a degree in the night sky as well. And we should know, hopefully, that a complete circle is 360 degrees, and that, for example, a right angle, which could be an angle between the horizon and the vertical, is 90 degrees, just for example. So this gives you an idea of how big some objects might be in terms of their angular sizes. The sun and the moon are both about half of a degree. So note that the angular size does not by itself tell us an object's true size. It's just how big it appears in the sky. So the angular distance between a pair of objects in the sky is the angle that appears to separate them. For example, the angular distance between the pointer stars at the end of the Big Dipper's bowl is about 5 degrees. I don't know if that's in this image here. Nope. But if you look at the Big Dipper and you look at those two pointer stars, those two stars at the edge of the Big Dipper's bowl, that's about 5 degrees. So you can actually use your outstretched hand to make rough estimates of angles in the sky. So this is something really neat. You don't actually need a protractor or anything crazy like that. You don't have to hold up a protractor to the sky. This works for anybody that's not trying to do precise measurements, but if you take your hand and extend it to arm's length, so just stretch out your arm all the way and hold up your hand, you can use your hand to come up with a couple angles. On average, the width of your palm is about 10 degrees, the width of your index finger is about 1 degree, and then if you take your index finger and curl it and look at it sideways, each segment of your knuckle from the furthest point by your nail takes up 3, 4, and 6 degrees respectively. So if you outstretch your arm and hold your fingers or hands up in certain ways, you can use them to estimate angular sizes in the sky. So again, it's not going to help actual astronomers come up with any precise measurements, but it gives you a general idea of the angular sizes of objects. Now, we do, however, have to make precise measurements in astronomy. So we do come up with some terms and some ways to represent small angles. So for more precise astronomical measurements, we can subdivide each degree into 60 arc minutes. And we can also subdivide an arc minute into 60 arc seconds. So these aren't anything new. These are still measurements of angles, but they're just smaller than a degree. So, for example, here we have 1 degree. Notice that we can take that degree, and in this part here we're blowing that up, and we divide that 60 times. So if you take 1/60th of 1 degree, you have what we call an arc minute, which is represented by a little apostrophe. But if we're doing really precise measurements, you can also divide a single arc minute into an arc second, which is represented by a quote or two apostrophes. So this allows us to make very precise measurements. So we have degrees. We divide that 60 times to get an arc minute, but then we can divide that arc minute 60 more times to give us an arc second. So we typically give or abbreviates arc minutes with the symbol, again, apostrophe, and arc seconds with 2. And we can read a precise measurement in the sky using a combination of all three, degrees, arc minutes, and arc seconds. So we could read this 35 degrees, 27 arc minutes, and 15 arc seconds. So that'll give you a very, very precise angle. So just a heads up that if you ever hear arc minutes or arc degrees, this is what we're talking about. It's just a smaller degree. It's just something smaller than a degree. We don't use it a lot in this course, but if, again, just for reference, this is what it is. Now, I will throw one equation at you here on the next slide. You don't, again, have to memorize it much or maybe even use it at all, but it's very good to at least kind of understand. So this is our last slide, but it is a bit technical. So I keep saying that there is a difference between angular size and actual physical size, right? So the sun and the moon have the same angular size, about half of a degree, but we know the sun's actual size is bigger. So that kind of a situation is happening in this top image here. We see the same angular size for, just pretend this is the moon and this is the sun. They both appear to have the same angular size, even though the sun is bigger. But the reason that happens is it's further away. So notice that this angle is the same for both. But the sun's bigger, but it appears to be the same angular size because it's further away. So there's actually an equation that can relate these different things. It can relate angular size and physical actual size. So an object's physical size does not change as you move it further away from your eye, right? It's just its actual size, the physical size of an object. Its size does not change as you move it away. However, as you move an object further away from you, its apparent or angular size does decrease, right? So let's say this is the moon again and you have it close to you. Well, say you take the moon and move it to as far away as the sun. Well, that angular size now is the dashed line is smaller because to you it looks smaller even though its physical size has not changed. So an object with an angular size given by this alpha symbol is a distance d away. So here is the distance lowercase d. So at a distance of d, it has this angular size. We can then use this following equation, known as the small angle formula, to figure out how big it actually is, capital D. So this is actually remarkable. If you know how far away an object is, and you just look at it and say, well, it's this big in terms of its size in angular measurements, you can figure out its true physical size. So this is huge. It's a very simple equation, relatively speaking, but it allows you to figure out some incredible things. So you can also work backwards. If you know the actual size of the object somehow and you know the angular size, then you can work backward and maybe figure out how far away it is. So stuff like this is really important in astronomy. I will maybe toss some other equations at you in the future, but I don't really ever make you use them too much. So just be aware that, I want to throw these at you just for general understanding, and you can start to see how math plays a role into some of these things. So that is our 5th lecture. In our next lecture, we'll start to go into some more detail. We'll begin to start talking about things like motions of the moon and the seasons and things like that. So thanks for watching, and I'll see you in the next video. Take care.